Mojave Desert, California, March 15, 2024. The morning sun cast long shadows across the barren landscape of the Mojave Desert as Dr. Michael Harrison stepped out of his research vehicle. At 42, the seasoned geologist had spent nearly 2 decades studying some of the most extreme environments on Earth, but nothing had prepared him for what he was about to discover in one of North America's most unforgiving terrains. Harrison had arrived at the remote coordinates as part of a routine geological survey commissioned by the California Department of Water Resources. The state was conducting comprehensive groundwater assessments across the desert region, searching for potential aquifer sources that might help alleviate the ongoing drought conditions plaguing Southern California. What started as a standard morning of soil sampling and rock core extraction would soon evolve into one of the most significant scientific discoveries of the decade. So glad to have you here. Comment your city so I can bring cases from your region and also know where you're watching me from. The temperature gauge on Harrison's equipment read 89 degrees Fahrenheit at 8:30 a.m., typical for mid-March in this section of the Mojave. The landscape stretched endlessly in all directions, a seemingly lifeless expanse of sand, scattered Joshua trees, and weathered rock formations that had stood sentinel over the desert for millions of years. This particular site, designated as Grid Reference MJ2847, lay approximately 47 miles northeast of Barstow, accessible only by a narrow dirt road that wound through rugged terrain. Harrison began his methodical work, using a portable drilling rig to extract core samples from depths ranging between 15 and 30 feet below the surface. The initial samples revealed the expected composition: compacted sand, trace minerals, and the occasional fossil fragment typical of ancient lakebed sediments. However, as he reached the 22-foot mark, his drill bit encountered unexpected resistance. The drilling equipment's sensors immediately registered anomalous readings. The temperature probe, designed to measure subsurface thermal conditions, began displaying numbers that seemed impossible for this environment. While surface temperatures soared toward triple digits, the readings from just over 20 feet underground showed a consistent 28 degrees Fahrenheit, well below the freezing point of water. Harrison initially suspected equipment malfunction. He withdrew the probe, checked the calibration, and ran diagnostic tests on all instruments. Everything appeared to be functioning correctly. When he lowered the temperature sensor back into the same hole, the readings remained consistent, a pocket of permanently frozen conditions existing beneath one of the hottest deserts in North America. Intrigued and puzzled, Harrison expanded his sampling area. Over the next 4 hours, he drilled 17 additional test holes in a grid pattern spanning roughly 200 square meters. The results defied conventional geological understanding. Every hole that reached depths between 20 and 30 feet encountered the same phenomenon: a subsurface layer where temperatures remained consistently below freezing, creating conditions that should not exist in this environment. More perplexing still were the core samples themselves. Mixed within the expected desert sediment were crystalline formations that appeared to be ice, but ice unlike anything Harrison had encountered in his professional career. These formations displayed unusual optical properties, refracting light in ways that suggested a different molecular structure than ordinary frozen water. The ice fragments remained stable even when brought to the surface, showing no signs of melting despite exposure to the desert heat. Harrison carefully preserved each sample in specialized thermal containers and documented their exact extraction coordinates. His field notes recorded not only the temperature anomalies, but also subtle variations in electromagnetic readings that his equipment detected near each drilling site. The magnetic compass showed minor deflection patterns, suggesting the presence of unusual mineral deposits or possibly metallic concentrations beneath the surface. As the afternoon progressed, Harrison noticed other environmental anomalies that he had initially overlooked. The sparse vegetation in the immediate area exhibited characteristics inconsistent with typical desert plant adaptation. Several species of cacti and drought-resistant shrubs showed signs of increased moisture availability, their root systems extending deeper than normal, and their cellular structure indicating access to consistent water sources. Weather monitoring equipment that Harrison had installed upon arrival began recording microclimatic variations that challenged his understanding of desert meteorology. Despite the broader region experiencing standard high-pressure conditions with minimal humidity, the air immediately above his drilling sites showed elevated moisture content and temperature fluctuations that occurred in regular, almost rhythmic patterns. Perhaps most intriguing was the discovery of biological activity in areas where life should struggle to exist. Soil samples from the surface layer revealed microbial communities that typically thrived in much cooler, wetter environments. These organisms appeared to be forming complex symbiotic relationships with the unusual ice formations, creating microscopic ecosystems that sustained themselves through mechanisms that remained completely mysterious. Harrison's training and experience told him that these findings warranted immediate expert consultation. The implications of discovering permanently frozen conditions in one of North America's most arid regions extended far beyond basic geological curiosity. Such phenomena could represent previously unknown hydrological processes, unique mineral formations, or even evidence of subsurface water systems that might revolutionize understanding of desert geology. Before departing the site, Harrison established a temporary monitoring station equipped with continuous data collection instruments. Temperature sensors, humidity monitors, and seismic detection equipment would provide round-the-clock surveillance of the area, transmitting real-time information to his laboratory facilities in Riverside. He also installed motion-activated cameras to document any surface changes that might occur over time. The drive back to civilization gave Harrison time to consider the broader implications of his discovery. If these conditions existed at this location, similar phenomena might be present at other sites throughout the desert region. The potential impact on water resource management, climate research, and desert ecology could be transformative for multiple scientific disciplines. That evening, Harrison contacted Dr. Jennifer Walsh, a climatologist at the University of California, Davis, whose research focused on extreme weather phenomena and climate anomalies. Walsh's expertise in atmospheric science and her extensive fieldwork in challenging environments made her an ideal collaborator for understanding the complex factors that might be creating these impossible conditions in the Mojave Desert. As Harrison prepared his preliminary report and organized the collected samples for laboratory analysis, he remained unaware that his discovery represented just the beginning of a scientific investigation that would challenge fundamental assumptions about Earth's climate systems and ultimately reveal secrets that had remained hidden beneath the desert for thousands of years. University of California, Davis, March 18, 2024. Dr. Jennifer Walsh arrived at her laboratory before dawn, her mind racing with possibilities as she prepared to examine the samples that Dr. Michael Harrison had delivered the previous evening. The climatologist's reputation for solving atmospheric mysteries had been built over 15 years of fieldwork in some of the world's most challenging environments, from Antarctic ice sheets to Saharan heat waves. However, the preliminary data that Harrison had shared suggested she was about to encounter something unprecedented in her career. The specialized analysis equipment hummed to life as Walsh began her systematic examination of the ice samples. Under high-powered microscopy, the crystalline structures revealed intricate patterns that deviated significantly from normal ice formation. The molecular arrangement displayed characteristics that indicated formation under extreme pressure conditions, yet the samples had been extracted from relatively shallow depths where such pressures should not exist. Spectroscopic analysis revealed even more puzzling results. The ice contained trace elements typically associated with deep groundwater systems, including mineral compositions that suggested contact with rock formations found hundreds of feet below the surface. Most intriguingly, isotopic analysis indicated that the water molecules had undergone unusual environmental processes, showing signatures that normally required thousands of years of specific atmospheric and geological conditions to develop. Walsh's investigation took an unexpected turn when she discovered microscopic biological material embedded within the ice matrix. These weren't simple bacterial colonies that might have been trapped during formation, but complex microorganisms that appeared to be actively thriving within the frozen medium. The cellular structures showed adaptations for survival in extreme cold, Yet their metabolic processes indicated they were somehow maintaining activity despite being encased in solid ice. Recognizing that these biological discoveries exceeded her expertise, Walsh contacted Dr. David Chen, a microbiologist at Stanford University, whose research focused on extremophile organisms. Chen specialized in studying life forms that survived in conditions previously thought to be uninhabitable, including organisms found in Arctic permafrost and deep ocean thermal vents. His laboratory possessed the specialized equipment necessary to properly analyze these unusual microbial communities. Chen's arrival at Walsh's laboratory marked the beginning of a collaboration that would expand the investigation far beyond its original scope. Initial examination of the microorganisms under electron microscopy revealed cellular structures unlike anything documented in existing scientific literature. These organisms possessed unique protein configurations that allowed them to maintain metabolic activity at temperatures that should have completely halted biological processes. Genetic sequencing of the microorganisms produced results that challenged fundamental understanding of life's adaptability. The DNA analysis showed evolutionary markers indicating these organisms had been isolated from mainstream biological development for potentially tens of thousands of years. Yet their cellular machinery was remarkably sophisticated, possessing mechanisms for energy production and reproduction that operated efficiently in sub-freezing conditions. More remarkable still was the discovery that these microorganisms appeared to be actively modifying their environment. Chemical analysis of the ice medium showed elevated concentrations of antifreeze proteins and specialized compounds that the organisms were producing to maintain optimal living conditions. They had essentially created a biological system that could sustain itself indefinitely within the frozen matrix, forming a self-contained ecosystem that defied conventional biological understanding. Meanwhile, the continuous monitoring equipment that Harrison had installed at the desert site began transmitting data that added new dimensions to the mystery. Temperature fluctuations followed distinct patterns that repeated every 12 hours, with subsurface conditions becoming slightly warmer during specific periods before returning to their baseline frozen state. These thermal cycles occurred independent of surface weather conditions or solar heating patterns. Electromagnetic readings from the monitoring station revealed regular pulse patterns that suggested the presence of organized energy sources beneath the surface. The signals followed mathematical sequences that implied natural resonance phenomena, possibly related to underground water movement or unusual mineral formations. Most significantly, these electromagnetic pulses appeared to correlate directly with the thermal cycling, suggesting a connected system of environmental processes. Atmospheric monitoring equipment detected trace gases being released from the surface at regular intervals. Mass spectrometry analysis of these emissions revealed compounds typically associated with deep Earth processes, including gases that normally required significant geological activity to reach the surface. The presence of these substances indicated that the frozen subsurface layer was connected to much deeper geological systems than initially suspected. Walsh expanded her investigation by analyzing satellite imagery of the broader Mojave Desert region, searching for similar environmental signatures that might indicate additional sites with comparable characteristics. Advanced thermal imaging revealed subtle temperature variations across several locations spanning a roughly 50-mile radius from Harrison's original discovery point. These thermal anomalies formed distinct geometric patterns that suggested organized subsurface structures rather than random geological phenomena. Ground-penetrating radar surveys conducted by Harrison's team revealed extensive underground cavity systems beneath the frozen layer. These cavities appeared to form interconnected networks that extended far beyond the immediate discovery site. Three-dimensional mapping of these subsurface structures showed chambers and tunnels that followed surprisingly regular geometric patterns, suggesting either natural formation processes that remained unknown to science or possible artificial construction. The biological samples continued to yield unexpected results as Chen's analysis progressed. The microorganisms demonstrated remarkable communication capabilities, releasing chemical signals that triggered coordinated responses throughout their communities. When samples from different extraction points were combined, The organisms showed recognition patterns that indicated they belonged to a single, extensive biological network that spanned the entire subsurface area. Perhaps most intriguingly, the microorganisms appeared to respond to environmental changes in ways that suggested sophisticated sensory capabilities. When exposed to variations in temperature, pressure, or chemical composition, they adjusted their metabolic processes and chemical production to maintain optimal conditions not just for their own survival, but for the stability of the entire ice formation system. As the investigation entered its second week, the accumulated evidence pointed toward the existence of a complex, interconnected system that operated according to principles that challenged existing scientific understanding. The frozen subsurface layer was not simply an isolated geological anomaly, but rather a component of a larger environmental mechanism that had been maintaining stable conditions beneath the desert for an unknown period of time. Walsh's atmospheric modeling suggested that the system was actively influencing local weather patterns in subtle but measurable ways. The regular release of moisture and specific compounds was creating microclimatic conditions that extended several feet above the surface, providing just enough environmental modification to support the unusual plant life that Harrison had observed during his initial survey. The implications of these discoveries extended far beyond academic curiosity. If this natural system could maintain frozen conditions and support complex biological communities in one of Earth's most hostile environments, it represented a potential breakthrough in understanding environmental adaptation and climate resilience. The mechanisms at work beneath the Mojave Desert might hold keys to addressing some of humanity's most pressing environmental challenges. However, as the research team prepared to expand their investigation with more comprehensive fieldwork, the monitoring equipment began detecting new types of activity beneath the surface. Seismic sensors registered movement patterns that suggested the underground system was much larger and more active than anyone had imagined, and preliminary analysis indicated that their scientific activities might have triggered responses from whatever lay hidden in the depths below. Mojave Desert Field Site, March 25, 2024. Dr. Sarah Thompson adjusted the ground-penetrating radar equipment as the early morning sun painted the desert landscape in shades of gold and amber. As the lead geophysicist on what had rapidly evolved from a routine geological survey into one of the most intriguing scientific investigations of the decade, Thompson brought 15 years of experience mapping subsurface structures in challenging environments around the globe. Her expertise in analyzing underground formations would prove crucial in unraveling the mystery that lay beneath this seemingly barren stretch of the Mojave Desert. The seismic data collected over the previous week had revealed something extraordinary. Beneath the frozen layer that Dr. Harrison had initially discovered, advanced imaging technology had detected a vast network of natural cavities that extended far deeper into the earth than anyone had anticipated. These underground chambers formed an intricate system of interconnected spaces that spanned an area of approximately 12 square miles, with some cavities reaching depths of over 300 feet below the surface. Thompson's team had established a comprehensive monitoring grid across the site, deploying sophisticated sensors capable of detecting the slightest geological movements and mapping subsurface structures with unprecedented precision. The three-dimensional images generated by their equipment revealed a complex underground architecture that defied conventional understanding of natural cave formation in desert environments. The cavities were not randomly distributed, as would be expected from typical erosion or geological processes. Instead, they formed geometric patterns that suggested organized structural development. The largest chambers were positioned at regular intervals, connected by smaller tunnels that maintained consistent dimensions and directional orientations. The overall layout resembled a sophisticated distribution network designed to facilitate movement of air, water, or other substances throughout the underground system. Most remarkably, the cavities showed evidence of active air circulation systems that operated independently of surface atmospheric conditions. Specialized sensors detected consistent airflow patterns that moved through the underground network, following predictable routes and timing sequences. The air temperature within these chambers remained constant at approximately 35 degrees Fahrenheit, regardless of external weather conditions or seasonal variations. Dr. William Rodriguez, a geologist specializing in underground hydrology, joined the investigation to analyze the water systems that appeared to be feeding the frozen surface layer. Rodriguez's initial survey of the underground network revealed an extensive aquifer system that connected to deep groundwater sources located hundreds of miles away. These water channels followed natural rock formations that had been shaped by geological processes occurring over thousands of years. The water flow patterns within the underground system demonstrated characteristics that challenged conventional hydrological understanding. Instead of following typical gravitational flow patterns, the water moved through the network in ways that suggested pressure-driven circulation systems. Temperature monitoring of the water sources revealed that liquid entering the chambers at significant depths underwent rapid cooling as it moved toward the surface, achieving freezing temperatures through processes that remained completely mysterious. Geological analysis of rock samples extracted from various depths revealed mineral compositions that provided clues about the system's formation timeline. The stone layers showed evidence of water contact dating back approximately 15,000 years, indicating that the underground network had been active since the end of the last ice age. However, the mineral deposits also contained elements that suggested much more recent geological activity, implying that the system had undergone significant changes within the past several centuries. The investigation took an unexpected turn when Thompson's team discovered that the underground chambers contained atmospheres with unusual gas compositions. Air samples extracted from various depths revealed elevated concentrations of gases typically associated with deep earth processes, including trace amounts of substances normally found only in volcanic or geologically active regions. These atmospheric conditions created environments that could support specialized biological communities while maintaining the stable temperatures necessary for permanent ice formation. Advanced thermal imaging of the underground network revealed heat signature patterns that indicated the presence of organized energy distribution systems. Certain chambers showed consistently higher temperatures than others, with thermal gradients that followed the geometric patterns identified in the cavity layout. These temperature variations suggested that the underground system was actively managing energy flow to maintain optimal conditions throughout the network. Perhaps most intriguingly, electromagnetic monitoring equipment detected regular signal patterns emanating from the deepest accessible chambers. These signals followed mathematical sequences that implied natural resonance phenomena, possibly related to the interaction between flowing water, mineral deposits, and the unique atmospheric conditions within the underground system. The electromagnetic pulses occurred at precise intervals and showed correlation with both the thermal cycles and the biological activity observed in the surface ice formations. Microbiological analysis of air and water samples from the underground chambers revealed the presence of the same extremophile organisms that had been discovered in the surface ice formations. However, the populations in the deeper chambers showed greater diversity and more complex community structures. These microorganisms appeared to be playing active roles in maintaining the chemical and thermal balance necessary for the entire system's operation. The biological communities in the underground network demonstrated sophisticated adaptation mechanisms that allowed them to thrive in the unique environmental conditions created by the interaction of cold air circulation, mineral-rich water sources, and stable atmospheric compositions. These organisms had developed symbiotic relationships not only with each other, but also with the geological and hydrological processes that sustained the underground system. As the investigation progressed, Thompson's team began to understand that they were documenting a natural phenomenon of extraordinary complexity and scale. The underground network represented a self-sustaining environmental system that had been operating for thousands of years, creating and maintaining conditions that should not exist in one of North America's most arid regions. The mechanisms at work involved precise interactions between geological, hydrological, atmospheric, and biological processes that functioned together with remarkable efficiency. However, the most significant discovery came when deep core drilling equipment reached the lowest accessible chambers in the underground network. At a depth of 287 feet below the surface, Thompson's team encountered evidence that transformed their understanding of the entire system. The deepest chambers contain not only the expected water and air circulation systems, but also physical structures that appeared to have been intentionally modified or constructed. Stone formations in the deepest chambers showed tool marks and geometric modifications that could not be explained by natural geological processes. These structural alterations suggested that ancient human populations had not only discovered the underground network, but had also developed sophisticated methods for enhancing and directing its natural processes. The implications of finding evidence of advanced engineering in a system that predated known technological capabilities challenged fundamental assumptions about prehistoric human knowledge and adaptation. The discovery of potential human involvement in the underground system's development raised profound questions about the true age and purpose of the network. If ancient populations had possessed the knowledge and skills necessary to modify and enhance such a complex natural system, it implied levels of environmental understanding and engineering capability that far exceeded conventional archaeological assumptions about prehistoric technological development. As Thompson's team prepared to conduct more extensive exploration of the deepest chambers, their monitoring equipment began detecting new types of activity throughout the underground network. The system appeared to be responding to their investigation activities in ways that suggested it remained capable of adaptation and change. Whatever secrets lay hidden in the depths of the Mojave Desert, the research team was about to discover that their scientific inquiry had awakened something that had been dormant for centuries. Archaeological Excavation Site, Mojave Desert, April 2, 2024. Dr. James Mitchell carefully brushed sediment away from what appeared to be a carved stone surface, his trained eyes recognizing patterns that would fundamentally alter the trajectory of the investigation. As one of the Southwest's leading experts in pre-Columbian archaeology, Mitchell had been called to the site after Thompson's team discovered evidence of human modification in the deepest chambers of the underground network. What he was about to uncover would challenge everything the scientific community believed about ancient technological capabilities and environmental knowledge. The excavation had begun 3 days earlier when ground-penetrating radar revealed large stone structures buried beneath centuries of sediment accumulation. These structures were positioned directly above the underground network's most significant chambers, suggesting an intentional relationship between surface constructions and the subsurface systems. Mitchell's team used precise archaeological techniques to expose these buried formations while preserving every detail that might provide insights into their origins and purpose. The first structure to emerge from the excavation was a circular stone platform, approximately 20 feet in diameter, constructed from precisely fitted blocks of local sandstone and volcanic rock. The craftsmanship displayed sophisticated understanding of engineering principles, with each stone shaped and positioned to create a level surface despite the uneven terrain beneath. Most remarkably, the platform incorporated a complex drainage system that directed water flow toward specific points that aligned perfectly with openings leading to the underground chambers. Carbon dating of organic materials found within the stone mortar indicated that the platform had been constructed approximately 800 years ago, during a period when the region was inhabited by advanced Native American civilizations. However, the construction techniques and mathematical precision of the stonework suggested technological capabilities that exceeded what archaeological evidence had previously indicated for populations in this region during that time period. As the excavation expanded, Mitchell's team uncovered a series of stone channels and conduits that formed an intricate water management system. These engineered waterways were designed to capture and direct the minimal rainfall that occurred in the desert, channeling every drop toward the underground network with remarkable efficiency. The system included settling basins, filtration chambers, and distribution networks that demonstrated sophisticated understanding of hydraulic engineering principles. The most significant discovery came when excavation reached deeper levels beneath the stone platform. Mitchell's team uncovered a chamber that had been intentionally sealed with carefully fitted stone blocks, preserved intact for centuries beneath layers of sediment. When the seal was carefully removed, The chamber revealed an archive of information that provided unprecedented insights into ancient environmental knowledge and technological capabilities. The sealed chamber contained numerous stone tablets covered with intricate carvings that depicted detailed representations of the underground network, including accurate maps of chamber locations, water flow patterns, and seasonal variations in the system's operation. The precision of these representations indicated that ancient populations had conducted systematic studies of the underground network over extended periods, developing comprehensive understanding of its complex environmental processes. Perhaps most remarkably, the carved tablets included mathematical calculations and geometric diagrams that described methods for enhancing and controlling the natural processes within the underground system. These technical specifications detailed techniques for modifying airflow patterns, optimizing water circulation, and maintaining optimal temperature conditions throughout the network. The mathematical sophistication of these calculations rivaled modern engineering approaches to environmental system management. Additional tablets contained detailed astronomical observations and calculations that correlated celestial events with changes in the underground system's operation. These records indicated that ancient populations had identified connections between seasonal atmospheric patterns, lunar cycles, and the network's thermal and hydrological processes. They had used this knowledge to predict and prepare for variations in the system's performance, ensuring stable operation across extended time periods. The chamber also contained tools and artifacts that provided evidence of the technological methods used to modify and maintain the underground network. Stone implements showed evidence of use in precision carving and shaping work, while metal tools displayed craftsmanship that exceeded known metallurgical capabilities for the region during the estimated time period. Some tools incorporated design features that appeared to be specifically adapted for working in the confined spaces and unique environmental conditions of the underground chambers. Biological analysis of preserved organic materials in the sealed chamber revealed that ancient populations had developed sophisticated understanding of the extremophile microorganisms that inhabited the underground network. Plant and animal specimens showed evidence of selective cultivation and breeding programs designed to enhance the organism's environmental benefits. These biological management techniques had been used to optimize the microorganisms' roles in maintaining chemical balance and thermal stability throughout the system. The archaeological evidence indicated that multiple generations of ancient populations had been involved in developing and maintaining the underground network. Construction phases spanned several centuries, with each generation adding improvements and refinements based on accumulated knowledge and experience. The scale and continuity of this effort suggested that the network had been considered a vital resource that justified sustained investment of time, labor, and technological development. Most significantly, the carved tablets included detailed descriptions of the underground network's role in supporting human habitation in the desert environment. Ancient populations had used the system to create microclimatic conditions that enabled agriculture, water storage, and shelter from extreme weather conditions. The network had functioned as a comprehensive environmental management system that made sustainable human settlement possible in one of North America's most challenging environments. Analysis of plant remains found in various areas of the excavation revealed that ancient populations had successfully cultivated crops that should not have been able to survive in the desert climate. These agricultural achievements were made possible by the environmental modifications created by the underground network, which provided consistent moisture, temperature regulation, and soil enhancement that supported diverse plant communities. The archaeological discoveries transformed the scientific team's understanding of the relationship between the underground network and human history in the region. Rather than being simply a natural phenomenon that ancient populations had discovered and utilized, the network represented a sophisticated partnership between human engineering and natural processes. Ancient populations had not only understood the complex environmental systems, but had also developed methods for enhancing and directing those systems to meet human needs. As Mitchell's excavation continued to reveal the extent and sophistication of ancient environmental management techniques, the research team began to recognize that they were documenting evidence of technological and ecological knowledge that had been lost to history. The methods used to create and maintain the underground network demonstrated approaches to environmental stewardship that could provide valuable insights for addressing modern climate and sustainability challenges. However, the most disturbing discovery came when translation work on the stone tablets revealed warnings and cautionary information that ancient populations had included in their records. These warnings describe potential consequences of disrupting or interfering with the underground network's delicate environmental balance. The tablets indicated that previous attempts to modify or extract resources from the system had resulted in catastrophic failures that led to environmental disasters and population displacement. As the research team continued their analysis of the archaeological evidence, seismic monitoring equipment began detecting increasing levels of activity throughout the underground network. The careful excavation and exploration activities appeared to have triggered responses within the system that ancient populations had specifically warned against. Whatever safeguards and protective measures had been established centuries ago were beginning to fail, and the team was about to discover that some knowledge had been deliberately buried for compelling reasons. Emergency Response Center, Mojave Desert, April 8, 2024. Dr. Jennifer Walsh stared at the comprehensive data analysis displayed across multiple monitors in the hastily established command center, her scientific mind struggling to process the magnitude of what the research team had uncovered. 6 days had passed since the archaeological discoveries revealed ancient warnings about disrupting the underground network, and those warnings were proving to be prophetically accurate. The system that had operated in delicate balance for centuries was beginning to exhibit signs of destabilization that threatened to transform their groundbreaking scientific discovery into an environmental catastrophe. The seismic monitoring equipment had been recording increasingly intense activity throughout the underground network since the excavation activities had reached the deepest sealed chambers. What had begun as minor tremors and pressure fluctuations had escalated into organized system-wide responses that indicated the entire network was undergoing fundamental changes. The sophisticated environmental balance that had maintained frozen conditions and supported complex biological communities was rapidly deteriorating. Temperature readings from sensors positioned throughout the underground chambers showed dramatic variations that broke patterns established over thousands of years. The consistent 35-degree temperatures that had characterized the network were fluctuating wildly, with some chambers reaching near boiling conditions while others dropped to temperatures that threatened to destroy the carefully balanced ecosystems. These thermal instabilities were creating pressure differentials that were causing structural damage to the ancient engineering modifications. Dr. David Chen's biological monitoring revealed that the extremophile microorganisms were responding to the environmental changes in ways that amplified the system's instability. The organisms had evolved sophisticated chemical communication networks that enabled coordinated responses across the entire underground system. However, instead of working to restore balance as they had for millennia, the organisms were now producing compounds that accelerated the breakdown of the ice formations and destabilized the water circulation systems. The atmospheric monitoring equipment detected massive releases of gases that had been trapped within the underground chambers for centuries. These emissions included greenhouse gases in concentrations that could significantly impact regional climate patterns if released into the atmosphere in large quantities. More concerning were trace amounts of gases that indicated deep geological processes were being activated, suggesting that the network's disruption was triggering responses from much deeper Earth systems. Dr. Sarah Thompson's geological analysis revealed that the underground network was connected to fault systems that extended far beyond the immediate desert region. The pressure changes caused by the network's destabilization were creating stress patterns along these geological connections, with seismic activity being detected at distances of over 200 miles from the original site. The ancient engineering had been designed to work in harmony with these deep geological systems, but the current disruption was threatening to trigger much larger-scale geological events. The team's understanding of the true scope and significance of the underground network crystallized as they analyzed the complete archaeological record. The ancient populations had not simply discovered and enhanced a natural phenomenon, but had created a sophisticated climate management system that influenced weather patterns across a vast region of the southwestern United States. The network had been functioning as a massive natural air conditioning system that helped regulate temperature and moisture conditions across thousands of square miles. Historical climate data analysis revealed correlations between the network's operation and documented weather patterns dating back over 800 years. During periods when the system had operated optimally, the region had experienced more moderate temperatures and more consistent precipitation patterns. Conversely, historical records of extreme weather events and drought conditions corresponded to periods when archaeological evidence suggested the network had experienced disruptions or maintenance problems. The implications of these discoveries extended far beyond academic interest. The underground network represented a natural climate regulation system that had been moderating environmental conditions across a significant portion of the American Southwest for centuries. Its destabilization could trigger changes in regional weather patterns that would affect agriculture, water resources, and human populations across multiple states. Dr. William Rodriguez's hydrological analysis revealed that the network was connected to aquifer systems that supplied water to communities hundreds of miles away. The disruption of water circulation patterns within the underground chambers was already affecting pressure and flow rates in these distant water sources. Several municipal water systems had reported unusual fluctuations in well performance and water quality that correlated directly with the timing of the network's destabilization. The research team realized that their investigation had inadvertently triggered the collapse of a system that ancient populations had spent centuries perfecting and maintaining. The warnings found in the sealed archaeological chambers had specifically described the catastrophic consequences of disturbing the network's delicate balance without proper knowledge and preparation. The ancient engineers had understood that the system required constant maintenance and careful management to prevent exactly the kind of cascading failures that were now occurring. Emergency consultations with climatologists and environmental engineers from universities and government agencies across the country confirmed the team's worst fears. The disruption of the underground network was beginning to affect atmospheric circulation patterns in ways that could trigger significant weather anomalies throughout the western United States. Computer models predicted that complete system failure could result in temperature increases of 3 to 5 degrees Fahrenheit across the region, along with dramatically reduced precipitation that could exacerbate drought conditions for decades. The biological consequences of the network's collapse were equally concerning. The extremophile organisms that had played crucial roles in maintaining the system's balance were dying in massive numbers as their carefully regulated environment deteriorated. These organisms had evolved unique genetic characteristics that made them invaluable for biotechnology research and environmental applications. Their extinction would represent not only an ecological disaster, but also the loss of biological resources that could have contributed to solutions for climate change and environmental remediation. As the situation continued to deteriorate, the research team recognized that they faced an unprecedented challenge. The ancient knowledge necessary to restore and maintain the underground network had been lost for centuries, yet the consequences of allowing the system to collapse completely extended far beyond the immediate desert region. They needed to find ways to stabilize the network using modern technology and scientific understanding, while respecting the sophisticated principles that ancient populations had developed through centuries of careful observation and engineering. The team's efforts to develop emergency stabilization measures were complicated by the scale and complexity of the underground system. The network encompassed hundreds of interconnected chambers spread across 12 square miles, with environmental conditions that varied significantly from location to location. Any intervention would need to address multiple interconnected processes simultaneously, requiring coordination between geological, hydrological, atmospheric, and biological systems that operated according to principles that modern science was only beginning to understand. International attention began focusing on the Mojave Desert site as news of the discovery and its implications spread through the scientific community. Environmental agencies from multiple countries offered assistance and resources, recognizing that the lessons learned from this situation could have global applications for climate management and environmental engineering. However, the urgency of the situation left little time for extensive consultation or collaborative planning. The most disturbing development came when deep monitoring equipment detected that the system's collapse was triggering responses from geological formations that extended far deeper than anyone had realized. Seismic activity was being detected at depths that suggested connections to major fault systems and possibly even deep magma chambers. The ancient warnings had mentioned consequences that extended far beyond environmental changes, and the research team was beginning to understand that they might have awakened geological processes that could reshape the entire regional landscape. International Climate Research Center, Mojave Desert, April 15, 2024. The massive coordinated response effort that had transformed the remote desert site into an international scientific command center represented the largest emergency environmental intervention in modern history. Teams of experts from 17 countries worked around the clock to implement stabilization measures based on the ancient engineering principles discovered in the archaeological excavations, while simultaneously developing modern technological solutions to prevent the complete collapse of a system that had regulated climate across the American Southwest for nearly a millennium. Dr. Michael Harrison stood before a wall of monitors displaying real-time data from over 300 sensors positioned throughout the underground network, watching as the carefully orchestrated intervention efforts began to show their first signs of success. The temperature fluctuations that had threatened to destroy the entire system were gradually stabilizing as teams of engineers implemented modified versions of the ancient water circulation techniques, using modern materials and precision controls to recreate the delicate balance that had been maintained for centuries. The breakthrough in understanding the network's operation had come when Dr. Jennifer Walsh's team successfully decoded the mathematical relationships described in the ancient stone tablets. The calculations revealed that the system operated according to complex feedback mechanisms that required precise coordination between thermal, hydraulic, and biological processes. Ancient engineers had developed methods for monitoring and adjusting these relationships using techniques that were remarkably sophisticated despite their apparent simplicity. Modern implementation of these ancient principles required the development of entirely new technological approaches that combined traditional engineering methods with advanced materials science and computer-controlled precision systems. Teams of engineers worked to install updated versions of the stone channels and pressure regulation systems, using specially designed ceramics and metals that could withstand the extreme conditions within the underground chambers, while providing the exact environmental controls that the ancient designs had achieved. The biological restoration effort proved to be equally challenging and crucial to the network's recovery. Dr. David Chen led international teams of microbiologists in developing cultivation techniques for the extremophile organisms that had nearly been extinct during the system's collapse. Laboratory facilities established at the site used advanced biotechnology methods to rebuild the microbial communities that were essential for maintaining chemical balance throughout the underground chambers. The organism's recovery demonstrated remarkable resilience and adaptability once optimal environmental conditions were restored. Within days of the system's stabilization, the microorganisms began re-establishing their complex communication networks and resuming their roles in regulating temperature, moisture, and chemical composition throughout the underground system. Their rapid recovery provided crucial biological support for the engineering interventions that were restoring physical infrastructure. Dr. Sarah Thompson's geological team worked to repair and reinforce the structural modifications that had been damaged during the system's destabilization. Using ground-penetrating imaging and precision drilling techniques, engineers accessed damaged areas of the underground network and installed modern equivalents of the ancient stone supports and pressure distribution systems. These repairs required developing new construction methods that could work in the confined spaces and extreme environmental conditions of the underground chambers. The archaeological insights provided by Dr. James Mitchell's team proved invaluable for understanding the maintenance requirements that would be necessary to prevent future system failures. The ancient records contained detailed protocols for monitoring and adjusting the network's operation across seasonal variations and long-term environmental changes. These protocols were adapted for modern implementation, using automated sensor networks and computer-controlled response systems. International collaboration on the restoration effort led to the development of new technologies and scientific approaches that had applications extending far beyond the immediate crisis. The methods developed for monitoring and controlling complex environmental systems in extreme conditions provided breakthrough capabilities for climate management, environmental remediation, and sustainable technology development. Research institutions around the world began implementing variations of these approaches for addressing local environmental challenges. The successful stabilization of the underground network confirmed its crucial role in regional climate regulation and opened new possibilities for understanding and managing large-scale environmental systems. Atmospheric monitoring revealed that the system's restoration immediately began affecting weather patterns across the southwestern United States, with more moderate temperatures and improved precipitation distribution returning to patterns that had been documented in historical records. The biological discoveries from the network yielded revolutionary advances in biotechnology and environmental science. The extremophile organisms provided genetic resources for developing new approaches to environmental cleanup, climate adaptation, and sustainable energy production. Laboratory studies revealed that these organisms possessed capabilities for breaking down environmental pollutants, producing useful compounds, and creating self-sustaining biological systems that could operate in challenging environments. International recognition of the network's significance led to its designation as the world's first ancient climate engineering heritage site, with protected status under international environmental agreements. The site became a focal point for research into historical environmental management techniques and their applications for addressing modern climate challenges. Educational and research programs were established to ensure that the knowledge gained from the investigation would be preserved and applied for future environmental stewardship. The economic implications of the discoveries extended far beyond scientific research. The technologies developed during the restoration effort created new industries focused on environmental engineering, biotechnology applications, and sustainable climate management. Companies around the world began licensing and adapting the innovations that had emerged from the crisis, generating economic benefits that helped fund continued research and development efforts. Long-term monitoring systems were established to ensure the network's continued operation and to provide early warning of any future destabilization risks. These monitoring capabilities incorporated both modern sensor technologies and traditional observation methods derived from the ancient maintenance protocols. International agreements established cooperative frameworks for managing and protecting the system while enabling continued research and technological development. The transformation of scientific understanding that resulted from the investigation extended across multiple disciplines and research institutions. Universities worldwide integrated the discoveries into their curricula, training new generations of scientists and engineers in approaches that combined traditional knowledge with modern technological capabilities. The interdisciplinary collaboration methods that had been essential for the restoration effort became models for addressing other complex environmental challenges. The network's successful restoration and the international cooperation that made it possible demonstrated the potential for combining ancient wisdom with modern science to address contemporary environmental crises. The principles and technologies developed during the effort provided blueprints for creating and managing large-scale environmental systems that could help mitigate climate change impacts while supporting human development needs. As the immediate crisis subsided and the underground network returned to stable operation, the research team reflected on the profound implications of their discovery. What had begun as a routine geological survey had evolved into a revelation that ancient populations had possessed environmental knowledge and engineering capabilities that rivaled or exceeded modern technological approaches. The successful integration of ancient principles with contemporary science had created new possibilities for environmental stewardship that could transform humanity's relationship with Earth's climate systems. The Mojave Desert site continued to serve as a living laboratory where researchers from around the world studied the ongoing operation of the restored network. The lessons learned from the investigation and restoration effort established new paradigms for environmental science, archaeology, and international cooperation that would influence scientific research and environmental policy for generations to come. The discovery that had nearly triggered an environmental catastrophe had ultimately provided humanity with tools and knowledge that could help ensure a more sustainable future.